In this video, we will try to understand in the most simple way how oxygen is transported from the lungs to the tissues through circulation. We know that oxygen gets transferred from the alveoli to the pulmonary capillaries by means of diffusion across a pressure gradient. The partial pressure of oxygen at the alveoli is much higher than that in the pulmonary blood. The partial pressure of oxygen at the alveoli is about 104 millimeter of mercury, while that in the pulmonary blood is only 40 millimeter of mercury. Once inside the plasma of pulmonary capillaries, oxygen is carried in two forms. The bulk, around 98%, bind with hemoglobin to form oxyhemoglobin, and the remaining 2% is in dissolved form. Now, let us look into the lesser 2% dissolved oxygen into some detail. The amount of oxygen dissolved in blood is directly proportional to each partial pressure. For each millimeter of mercury of partial pressure of oxygen, 0.003 milliliter of oxygen gets dissolved in 100 ml of blood. So in 100 millimeter mercury of partial pressure of oxygen, 0.3 milliliter of oxygen gets dissolved in plasma. Another important fact is that it is actually the partial pressure of oxygen which is in saturated form that is measured in blood gas analysis like ABG, the arterial blood gas, or VBGs as the case may be, not the 98% bound to hemoglobin. We say that 98% of oxygen in the blood after diffusion from the alveoli is bound to hemoglobin. Now, the normal adult hemoglobin, that is HbA, is a 4 protein molecule with 2 alpha chains and 2 beta chains. Each protein chain is attached to one heme unit. Each heme is capable of reversely binding to one oxygen molecule at each ferrous atom. As each of the 4 heme units binds an oxygen molecule, it causes a change in the shape of the hemoglobin molecule, which in turn causes the other heme units to be more exposed. Now, as a result of this conformational change, there are two possibilities. One, the successive oxygen molecules may bind less tightly than the first to heme units. Two, the successive oxygen molecules may bind more tightly to hemes than the first. Similarly, the release of oxygen from heme units may become more easy or more difficult. The net result is the release of oxygen by hemoglobin as the partial pressure of oxygen in the surrounding plasma falls, or the uptake of oxygen by hemoglobin as the partial pressure of oxygen rises is not in a linear correlation with partial pressure of oxygen. It is curvilinear or sigmoid shape. Now, after knowing the volume of oxygen dissolved in plasma and the oxygen binding capacity of hemoglobin, we may calculate the oxygen content of blood if we know the hemoglobin concentration, the partial pressure of oxygen, and the percent saturation of hemoglobin of a person. Say, for example, in 100 ml of blood, hemoglobin is 15 gram. The saturation of hemoglobin is 100%, and the partial pressure of oxygen is 100 millimeter of mercury. Now, the oxygen content of a given volume of blood is the total of dissolved oxygen plus oxygen bound to hemoglobin as oxyhemoglobin. We know that for each millimeter mercury partial pressure of oxygen, 0.003 milliliter gets dissolved in plasma. So in our example, 100 millimeter mercury of partial pressure of oxygen multiplied by 0.003 gives us the volume of oxygen in dissolved form, that is 0.3 milliliter per 100 milliliter of blood. Now we know that each gram of hemoglobin contains 1.39 milliliter of oxygen, assuming all the four heme units are occupied by oxygen molecules. So if 1 gram of hemoglobin carries 1.39 milliliter of oxygen, 15 gram hemoglobin with a saturation of 100% will contain 20.85 milliliter of oxygen. The total oxygen content in 100 ml of blood then is 20.85 milliliter bound to hemoglobin plus 0.3 milliliter as dissolved form, 21.15 milliliter of oxygen per 100 ml of blood. Thank you for watching. Happy learning.